So hello, everyone. So thank you very much for coming to the third concluding class. And so today we're going to talk mostly about Grigorchuk group, but hopefully we're going to have a little bit more time to talk about some cryptographic applications, but we'll see how things will go. So yesterday we finished discussing the Wraith recursion, and so I touched base on how to solve the word problem using Wraith recursion. Basically, you just take an element and you develop the sections of this element along the tree until you see the repetition, because the length of the input word will not increase. That means that sooner or later you see the repetitions. And once you see the same section, the same word twice, that means that you can stop proceeding in this branching algorithm and just return to the next branch. Okay, so basically today, let me try to see if I can write here. Okay, so today, basically we're going to prove the theorem. So let G be ABCD. That's Grigorchuk group. That's the one that we defined last time. So, and I'll just repeat the Wraith recursion here because we're going to need it. So A is equal to 1, 1 sigma, and B is equal to B, sorry. No. B is equal to AC, C is equal to AD, and D is equal to B1, 1B. Okay, so then the theorem that we are going to prove today is the following. So theorem, Grigorchuk group is an infinite, finitely generated. Of course, it's clear that's finitely generated by definition. So I'll just try it finitely generated to group. Okay, so thus answering the Burnside problem. From 1902. Okay, so that's the problem that we started our mini course with, right? And so I hope that by the end of this lecture, you will be kind of amazed how easy the solution is. Well, it's not completely trivial. As I said, it was solved in 1964 first, the Burnside problem. So it took 62 years to solve this problem. And then there were some more examples of periodic groups. There were two more claims, one by Aleshin, one by Sushansky, also from Kiev, so using the construction of the iterated Wraith products as well. But this group is way simpler than anything else. So that's the beauty of this argument. Okay, so let's first try to, well, let's just dive into the proof. So we're gonna do the proof into a couple of. We're gonna split the proof into a couple of blocks. So first of all, before doing anything, let's just familiarize ourselves a little bit with this group. So, well, first of all, note that you have a squared is equal to b squared is equal to c squared is equal to d squared is equal to 1, right? So that's what we proved last time, just by developing the sections of a squared using the Wraith recursion over here. Yeah, by the way, so when I say over here, you probably do not see where I have my pointer, right? Probably so. Okay, so let's see. Do I have something like pointer here to point? Probably should, but I don't see it right now. No, that's the color. All right, so I will just, so this is wreath recursion, right? So I will be just referring to the wreath recursion on top. Okay, so and then the last thing that we've done last time, I mentioned that we can also check that BCD is also equal to 1, right? So if you start taking sections of BCD, so first of all, you will notice that none of the BCD is active, right? That's why the product of these three letters, the element BCD, will be acting trivially on the first level. Then once you start developing, right, you pass to the sections, and every time when you take the product of BCD in any order, on the left component, you're going to have a squared, which is equal to identity. And on the right side, you're going to have, again, BCD in some order. And so you will see that they commute BCD. And so that's why once you start developing further and further, you will see the product of BCD exactly in the same order after 3 steps. And that's where you stop. And then you make a conclusion that BCD is equal to identity. Okay, so, well, if that's the case, then that's already sufficient for us to conclude that, so then the group generated by B, C, and D, this is isomorphic to Klein group of size 4, which is just the same thing as Z2 squared, where Z2 is that's just a group of order 2. That's a abelian group of size 4, right? And whenever you see BC, you can replace it with D, and CB, that's the same thing as D. Whenever you see BD, that's C, and DB is also C. And finally, CD is B, and DC is also B. Okay, so now let's think how the elements of this group might be addressed, right? So let's see. So each element G in G, right, can be written, of course, as a product of A's, B's, C's, and D's. First of all, because the generators are involutions, there is no need to talk about inverses. Okay, so we'll not be able to access this whiteboard, so I'll probably try to save it somehow. Okay, so right, we don't have to talk about the inverses because every generator is its own inverse, right? So that's already very good. So then, because we have that squares of generators are equal to identities, there is no point to have any power of any generator more than 1, because of course everything will reduce to either 0 power or first power. So that's squared, of course. And second of all, because of these relations, right? So there's no point to have B or C or D together in pairs, because anytime you have them in pairs, you reduce it to a single generator, right? And so that's why each element of G can be represented by a word of the following form. So A, G, right, will be equal to. So maybe some letter B, C, D, then A, then some letter B, C, D, then A, some letter B, C, D, then A, and so on and so on and so on. Some letter B, C, D, and then A, and maybe at the end some letter B, C, D. Okay. So where star, every star belongs to B, C, D. Of course, different stars can be different. It's just to simplify the notation. And first and or last star may be missing. Okay, so this is all the standard form of an element, right? Of course, so you can check that this is not quite normal form because it's not unique. So note, one can check. So either using the standard algorithm for solution of a word problem, or using atom.grp package. So by the way, so one problem in the homework refers to atom.grp package. And in the notes, I have a short introduction into this package. And it's very useful when you actually do the calculations. One can check, for example, that AD to the fourth is equal to 1 in G, right? Oops. Sorry, guys. I'm just trying to see. Just malfunctions a little bit, but that's okay. So I think that we'll go through that. So because AD to the fourth is equal to 1 in G. So let me see. Oops. Yeah, there's a good question. Yeah, there's undo. Okay, good. Undo. Okay. So one can check that AD to the fourth is equal to 1 in G.
Because of b square b on each point vertex, yes?
Well, so you have to start developing AD to the fourth. Once you develop it on the level 1, right? So this A will go to identities, but these will be transformed into ones and Bs, and then you have to develop Bs and so on. So yeah, so there is a little bit of work to show that, but that's just the standard algorithm. Right, but in particular, so that means that AD will be equal to DA, right? So, and both of these words are in this canonical form, right? And we can see that they both represent the same element of the group. Okay, but that's okay. So we just have to understand that you can represent every element by this long word, but not necessarily in a unique way. That's fine. So now remember that in the Breath recursion, A was the only element that flipped the vertices of the first level. B, C, and D were not flipping those vertices, right? So you can define a subgroup. We will call it H, which is stabilizer in G of level 1, right? So stabilizer of the first level. Well, let's see. So what can we tell about this stabilizer? So it will contain all the words with even number of A's, right? Consisting of all elements in G that can be written with even number of A's. Okay. So clearly there's going to be a subgroup, right? Because stabilizer of anything is going to be a subgroup in any group, right? Moreover, so clearly that's going to be a subgroup of index 2 because the cosset representatives are just identity and A. If you have an element which is not in this group, you can just multiply it by A to get into this H, right? So moreover, the index of H in G is equal to 2 because transversal, the representatives of the cossets are 1A. Okay. And so in particular, you get that H will be a normal subgroup in G because every subgroup of index 2 is normal. All right, sounds good. So now clearly we can write down the generating set for this stabilizer, right? So if we want to have that the number of A's is even, so H H second. Okay, so H is generated by BCD and by the conjugates of BCD with A. So B to the A, C to the A, and D to the A, where B to the A is just ABA. That's the conjugate of B with A. Of course, normally in the conjugate you have A inverse, but of course, because A is involution, then there's no point to write A inverse, so that's why conjugate of A will be just ABA. Okay, why is that? Because if you have even number of A's in this word representing G, so you could just take this word and cut it in blocks containing either 0 or 2 A's, right? So, for example, if this star is present, you can cut that as a first block, then the second block, third block, and then 2 A's will go to the next block, and so on. And because the total number of A's is even, this chopping will be well defined, and you will be able to represent this G as the product of these 6 elements in some order. Okay, so that's very nice. And now let's try to see what are the decompositions of this BCD and B to the 8, C to the 8, D to the 8. Well, let's just compute one for example, B to the 8. We already know that B is equal to AC, right? C is equal to AD, and D is equal to 1B. Okay, so let's compute B to the A. B to the A, that's going to be 1, 1 sigma, that's ABA. Then you have AC, and then you have again 1, 1 sigma, which is A, right? So let's concentrate on, for example, doing this product first. So because this sigma flips the subtrace, right? So that's why you multiply this 1 by this C, and this 1 by this A, okay? And then you move sigma to the right. So that's why you get 1 times C, which is C, 1 times A, which is A, and then sigma, and then 1, 1, A. 1, 1 sigma again. So here we again have sigma over here, so that's why we have to multiply first component by the second component by the first component, right? And then we multiply sigma times sigma, so at the end of the day, we're going to get just C, comma A, and then sigma will cancel with the sigma, and that's going to be the final outcome, okay? So basically, what conjugation by A does is just flips the coordinates, because B was AC, while B to the A will be CA. Okay, so let's write it down. So this is going to be CA, and C to the A, just flip coordinates here, will be DA, and D to the A will be equal to B1. Okay, so now we have a proper subgroup in G, and also we have a map. So we have of course, this projection that we defined last time. So before we were talking about projection or embedding, not projection, from the full group of automorphism into a Rith product of this group with the symmetric group. But here you could actually do even better. You could say that there is an embedding from G to G Rith symmetric group of order 2, right? And if you take this psi and restrict it to H, you have psi restricted to H, it will be from H to, it will be actually embedding to G cross G. And this embedding is defined exactly by these formulas, right? So you have generators, B, C, D, and B to the A, C to the A, D to the A, right? So B got sent to AC, C got sent. I want to write that vertically because you will see it's going to be much easier to see that the group is infinite. AD, and D goes to 1B, and B to the A goes to CA, C to the A goes to DA, and D to the A goes to B1. Okay, so this is the map from a subgroup of index 2. Remember that this is a normal subgroup in G of index 2. To the product of the group with itself. And now let's just look at, for example, right side here, the first component. Take this map psi, and then take the projection onto the first component. So we see here, A, we see B, we see C, and we see D. So we see the whole group, right? Because now if you take products of these guys, that will correspond to products of the first components as well, right? So that's why you can get every element of G as the first component of some element in H, right? So clearly, if you take psi and then you take pi 1, that's going to be from H to G, where this is projection first component. Is onto, right? Okay, so what conclusion can we make? So we have an onto map from a subgroup of index 2 onto the whole group. So what can we derive right away? Any ideas?
This subgroup isomorphic to this group?
Well, it's not going to be actually isomorphic, but the point is that because it maps onto, if it were finite, if the full group was finite, then that couldn't happen, right? Because if G was finite, then subgroup would have half an elements compared to the whole group. And there's no way to have a surjection from a subgroup of index 2 onto the whole group if G was finite, right? So the conclusion that we make now is that G is infinite. Okay, so that's the first part of our theorem that we are proving. Remember that the proof here is that it's an infinite finitely generated two group. So we proved infinite. Oops. Let's see, maybe do we have the colors here? Okay, let's do blue. So we proved already infinite. Of course, what is that? Just it's probably too clever a little bit. Okay, so let's see. It's infinite. No. It's finitely generated. Okay, let's have triangles. That's fine. So the last thing that we are interested in, we want to check that it's actually a two group. Okay. So that's where we want to, yeah, I don't know. Maybe I've done some magic, something, I don't know. So let's see if I can still write. That's a marker. Smart drawing. No, if I don't want smart drawing, so how do I go back to the regular drawing? Okay, let's try to write. So we want to understand whether this group is a two group, right? So that's the last thing that we need to prove, and that's kind of the core of the argument, because it's quite easy to see that the group is infinite just because the projection of the subgroup of index 2 onto the group is onto actually. Okay, so let's try. So now, no, I think I switched to some mode, which I wasn't supposed to switch. So let's see. Basic shapes. No. Sorry, guys. So some technical issue to resolve. Okay. That's pen. Okay. Right? No, that's definitely not what I want. If you know, guys, how to change it, I will appreciate your help. If you can tell me what to press so that I get back to just a regular pen. Smart drawing.
Excuse me, can I ask a little question about form? Is it minimal length of words in this group?
No, not necessarily. So we're not claiming that this is a minimal length. So we just represent those.
I mean form A star, this form.
Right. So no, we're not claiming. So of course there is one word which is of minimal length of this form that represents every element for G. But we are not claiming that every word like that has minimal length. So there are multiple words that represent the same element that have this form.
Mm-hmm.
Okay. So let's see. G is infinite. No, that's not what I want. Basic shapes. No, I don't want to sign in. Yeah, okay, there we go. So I probably by mistake I pressed that. Okay, so now that's good. All right, so now we need to prove that G is a two-group. So we're going to do that by induction on the length of a word representing an element. So we will say that if an element can be represented by a word of some length, some fixed length, up to n, then we assume that it's going to be that it's going to have a finite order. Moreover, the claim is that this order will be a power of 2, right? So so we do that by induction. By induction on the length of a word representing G, right? So claim will be the following. Claim, let's say all words of length less than or equal to n, or let's say less than n, represent elements in G of orders of order 2 to the I for some I. Of course, depending on that element, right? So we assume that all words in this fixed nice form up to length n have order 2 to the I for some I. So, well, first we check the base. So we're doing induction, so standard argument. So base case, let's talk about words of order, words of length up to 2. So words of length less than or equal to 2. That's going to be our base case, and we can just do it manually. So you have identity, you have A, B, C, D, and then you have, of course, AB, AC, AD, and BA, CA, BA. That's all you have because you cannot mix BD together because that will immediately give you C, right? So we have 4, 5, 6, 7, 8, 9, 10 elements of length up to 2. So those are elements. And so the orders, you could compute it manually. So, of course, order of identity is 1. A, B, C, D have order 2, 2, 2, 2. And AB has order 16. You can check that. AC has order 8. AD has order 4. And same here. So 16, 8, and 4. All right. So can be checked either manually or with TomGRP in GAP. So there's another package called FR written by Laurent Bartholdi. So there is a big overlap between functionality of atom.grp and FR, but you could use either of those. Okay, so that's why base is done. Okay, so we know that all elements of up to length 2 that can be represented by words of up to length 2, we know that their orders are finite, and those orders are powers of 2, right? Well, so next thing is, of course, induction step. So assume claim is true for all words of length less than n, okay? And say you have an element G. G can be represented by this long word, right? So star A, star, and so on, star A, maybe star at the end, of length n. Okay, so we want to show that G also has a finite order, and that order is a power of 2. Okay, we have to consider a couple of cases, right? Well, so there is essentially only one case which is non-trivial, right? But all other cases can be reduced to that case, essentially. Okay, so case 1. So in this decomposition of G, either first one or the last one star may be missing, right? So let's do case 1 when, for example, you know that both of them are missing. G is equal to, let's say, A star, and so on, star A, right? So it begins with A and ends with A. Well, then we can do a little trick. So we can compute, for example, G to the A. We can conjugate G by A, right? So that means that you multiply by A inverse on the left and by A on the right. But A inverse on the left is just A. So you have A star, A star, and so on, star, A, right? Where this has length n, right? And of course, this A, because A has order 2, this kills that, and we are left with a word of a length n minus 2, which is definitely less than n, right? So that's why G to the A has length n minus 2. And thus has order 2 to the I, right, for some I. Right, so we are done because the order of G is the same as the order of G to the A, right? If G to the n is equal to 1, if you raise G to the A to that same order n or m, then of course this a's in the middle will cancel, and you'll see that the order of G is equal to the order of any of its conjugate. But order of G is equal to order of G to the A. So we're done with this case. That's why G also has order 2 to the I. Okay, so case 2. Any questions so far? All right. So case 2, well, so maybe G starts just with one A, for example, and is not finished with A, is finished with something else, right? So, no, maybe let's do that, both of them actually. So they both start from non-A. Okay, so let's do G is equal to, let's say, star 1, A, star, and so on, star, A, and then star 2. Okay, so maybe it's like B, A, something, A, C, for example, or maybe B, A, something, something, A, B, right? Well, then we do similar trick. We just conjugate by star 1. So let's say for star 1, star 2 in BCD. Okay. Well, so then if you conjugate G by star 1, so what do we get? So star 1 will be canceled in the beginning, right? So it's going to be star 1, A, star, and so on, A, star 2, and then star 1, right? So again, so we have that this length is n, right? So star 1 cancels, right? And star 2, star 1, that's the product of some BC or B squared. It's going to be either identity if star 1 is equal to star 2, or it's going to be just the third element in this Klein group, third non-trivial element in the Klein group. So this will be equal to star 3, where star 3 is in 1, B, C, D. Okay, so that's why the total length, so this G to star 1 has length less than or equal to n minus 1. So we again can apply induction assumption. So we again can apply induction assumption to conclude that the order of G to star 1, which is the same thing as order of G, is equal to 2 to the I for some I. Okay, so we've done case 1, we've done case 2. So now what is left is when it starts with A and ends with non-A, or maybe if it starts with non-A and ends with A. So that's case 3. And we're going to have 2 subcases in case 3. So case 3, G is equal to, let's say, A star, and so on, star A star. Okay, it starts with A and ends with non-A. Or G is equal to, maybe it starts with non-A and then goes with A star star A and ends with A, right? So clearly, if we do one of these cases, the other one is done as well, because if you take this element and conjugate it by A, you're going to get the element of this form, right? So enough to consider only, for example, this case. Enough to consider only this case as you then get the first case by conjugation by A. Okay. Okay, so that's kind of our assumption. So we're talking about this case. That's the most interesting case. And now we consider 2 subcases. So one will be easy, and the other one will be slightly more complicated. Just okay. So subcase 1, well, yeah, actually, we're going to consider kind of even not 2, but even 3 cases. No, I think it's 2. Yeah. Okay. I'll just write consider subcases, and then we're going to count. So consider, so I meant that was supposed to be black. Okay. So consider subcases. So subcase A. right? So it may happen that there is even number of A's. So number of A's, let's call this decomposition star, for example, right? Number of A's in star is even. Okay. So then we know that this G is in the stabilizer, right? And you can write it actually as the product of the generators of the stabilizer. So then we can just take this word, right, and chop it into these generators of the stabilizer, which we'll call syllabi. So it's going to be either one element that doesn't have any A, or it's gonna be A something A. So then we can write G as a product of, so let's see how many blocks of less than or equal to n plus 1 over 2 blocks from the generation set of the stabilizer, B, C, D, and then you have B to the A, C to the A, D to the A, right? Okay. And we know how these guys are decomposed, right? So B is decomposed is AC, C is AD, D is 1B, right? And we need this decomposition to see how what will happen with the sections of this element G when you consider the sections at the first level. And B to the A is CA, C to the A is DA, and D to the A is B1, right? So then, so we can write G as a product of at most n plus 1 over 2 blocks, right, from this set. And we can write G as G sub 0, G sub 1, right? And there is no non-trivial permutation here because we know that G is in the stabilizer in this case. So how do we form this G sub 0 and G sub 1? Well, so you just write down the decomposition of these blocks, right? And you take corresponding products of first components and then second components. The product of first components will form you G sub 0. The product of second components here will form you G sub 1, right? And so moreover, with the length of G sub I less than or equal to number of blocks, right? Because every block introduces exactly one letter to the left and one letter to the right, but sometimes one of these letters could be even trivial, so that's why it could be even less, right? But definitely it's going to be not more than the number of blocks, which is equal to n plus 1 over 2, which is less than n for n greater than 2. And that's exactly the case that we are considering because we already checked for n equals to 2 as the base case of induction. Okay, so what do we get? We get that G is decomposed as the product of two, is decomposed through two sections, right? And each of these sections has length less than n. So we can apply induction assumption. That means that this section has some order 2 to the L, this section has some order 2 to the M, but then the order of G will be just the 2 to the maximum of L and M, and also will be finite. So by induction assumption, you have that the order of G sub 0 will be 2 to the L. Order of G sub 1 will be equal to 2 to the M, let's say. So then the order of G will be equal to 2 to the max Lm. So we're done in this case. It's a finite order, which is a power of 2. So that was an easy subcase. So let's say we have subcase A. Now let's do subcase B. Well, so subcase B, of course, if is the case when the number of A's in star is odd, right? So number of A's in star is odd. Right? So remember that star was this decomposition. That's our case when G starts with non-A and ends with A. All right, so what do we do in this case? We do basically the same thing. So, but then the estimates will be slightly more complicated. So then, well, we can write G as HA, right? Where, so we kind of A, that's the coset representative for the non-trivial coset of the stabilizer. And H will be in the stabilizer with H in H, right? And we can write G as H0, H1, comma A, where H0 and H1 are just sections of H. Okay, so then what do we do? So we have then we can consider G squared, right? So we want to understand what's the order of G. So there is this A here, which is a little bit annoying, right? Because taking the order, taking the powers, right, will be messing with the permutation. So let's just compute G squared first. G squared, so again, so A is just a non-trivial permutation of the first letters of the input word, right? So that's why it's going to be H0, H1, A times H0, H1, A. And you can replace A with sigma, essentially. And again, we multiply, oops, interesting. Where did it go?
Is it dependence of order of G with number of A in components of element and
Yeah, of course. The more A you have, the higher the order will be. So yeah, so let me see here. And where's my whiteboard? Disconnected audio for tools, report apps, whiteboards, existing whiteboards. And do you see whiteboard right now or you don't? Yeah, I click on it, and for some reason I cannot access it. Sorry, guys, for a little more technical issue. So I don't want to. Do you see right now the whiteboard, or you don't see whiteboard? Can you tell me?
Yes, I
no,
see.
no, we see only right half of your board.
Okay. So that means that it's somewhere. Maybe here. Gallery, speaker. Okay, yeah, there we go. So I got back. Okay, so you have G squared is H0, H1, A, H0, H1, A. And so we just multiply according to the formula in the with product, right? So H0 is multiplied by H1, H1 is multiplied by H0. So you have H0, H1, H1, H0. And then A cancels with A because A has order 2. So that's it, right? So now we have an element in the stabilizer, but now we just have to estimate what is the length of H0, H1. If it happens that the length of H0, H1 is less than n, then we will be done because the order of H0, H1 will be finite, will be power of 2 by induction assumption. And the order of H1 is 0, H1, H0 is the same as the order of H0, H1 because H1, H0 is just conjugate of H0, H1. it's a cyclic conjugate. So, and once you take a conjugate, you don't change the order. So yeah, we're kind of closing to the end of the proof right now already, but that's kind of the key argument starts right now. Well, let's just try to understand what's the length. So it's enough to show that the order of H0, H1 is equal to 2 to the I, for some I, right? And we, of course, we want to apply induction assumption, right? So, well, let's try to estimate. So you have that the length of H0, H1, right? So again, H0, H1, H, right? Just like in case A, oops, again, something's wrong. I moved H. Okay, there we go. Okay, so remember that when we were in case A, when number of A's is even, we represented G as G0, G1, right? And then the length of each of these sections, G0 and G1, was less than or equal to number of blocks, right? And number of blocks was actually less than or equal to n plus 1 over 2, where n was the length. So it's kind of similar here, but the problem is that the length here will be n minus 1, right? Because if H ends with A, right, and that's our case right now, G ends with A, and so this has length n, right? Then H will have length n minus 1, right? So that's why in this estimate of the length of the section, we can say that this is less than or equal to length of H0 plus length of H1, right? And for each of them, the estimate will be exactly the same. So that's why this is going to be less than or equal to 2 times, and length of H0 will be 2 times n minus 1. Sorry, not 2, just n minus 1. Yeah, let me just do this really quick. Okay, 2 times n minus 1 plus 1 over 2. So we are using the same estimate as over here, as on top for the section of G sub I, right? So this section over here, n plus 1 over 2, but now we have n minus 1 instead of n. And if you calculate this, it's going to be just equal to n. Okay. And that's kind of a problem for us because we want to have something of length less than n to apply induction assumption. If this length is equal to n, we cannot apply induction assumption right away. But, of course, we have to be slightly more clever, right? And so I'll just write, so we cannot apply induction assumption directly. Okay. But we do the following thing. So if it happens that this length is less than 1, then we, of course, can apply it, right? So, well, we consider now a couple of things, right? So, since you have that D is equal to 1B, right? So whenever you have D in the original word, H, right, it will introduce 1 in one of these H0 or H1. And that's why the length will be strictly less than n. So if you want to have that there is equality everywhere, right, you must have that there are no D's in the original word. So if there is D, so of course you have D is equal to 1B, and ADA is equal to B1, right? So the only situation in which the length will be equal to n, so the only case when length of H0, H1 is equal to n is when there are no D's, there are no blocks with D. in H. Okay, sounds good. So that's why we rule out blocks with D. So then we are left with just blocks with C and B. So you could have either C or B or ACA or ABA. Okay. So, but if we have some block with C, right? If H involves a block with C, well, then, of course, we can decompose it, right? So we can decompose it further, right? We have C is equal to AD, and ACA is equal to DA, right? So then one of H0, H1 will have blocks with D. And so we are back to our previous subcase. So we are back to previous subcase. So again, we will have a finite order. Finally, if that is not the case, that means that we cannot have blocks with D and we cannot have blocks with C. So then the only thing that we are allowed to have is just blocks with B. So then, let's say otherwise, we are allowed to have only blocks with D, blocks with B. But then, of course, the word G will be just equal to BA, BA, and so on, BA, which is equal to BA to some power K. But this one has finite order because BA itself has finite order, which must have finite order 2 to the I, or I is in, say, 0, 1, 2, 3, and 4, as order of BA is equal to 16. And that finishes the proof, right? So in any case, we see that once we go down, the length of the sections will also go down. So we can apply induction assumption. We conclude that the sections have finite order, and then the order of the original element that we started with is expressed in terms of the orders of these sections, right? Right, so you have witnessed a very short and beautiful proof of a problem which was open for 62 years. And of course, unfortunately, I ran out of time, so that was just an introductory course. There is so much more to tell that I was not able to fit into this course. So there is a beautiful connection to complex dynamics through iterate monodromy groups. There are connections to computer science, to analysis on graphs, to so many other things. So I'll definitely encourage you to read more into that. I'll be happy to talk with you, answer questions. So just in case, my email is savchuk@usf.edu. So please feel free to write me emails. And I will also post kind of the ideas of solutions to the homework problems next week. So I will mention just a couple of things in the homework problems. In the second homework, I listed 3 last problems, which are a bit more complicated. So 2 of them are not terribly complicated, terribly more complicated. But the third one, so that's kind of an open-ended. I know the solution, but the solution comes from complete understanding of the structure of this group. So I was curious, maybe someone will find some easier way to find that an element has infinite order. So I will be looking forward to your ideas. So there are lots of open questions in the field. Yeah, so probably let me conclude here, and let me thank you for your participation.